Welcome to a session on determination of carrier concentration in an intrinsic semiconductor. So to determine the carrier concentration in an intrinsic semiconductor, it involves three crucial steps. Step number one is to determine the density of electrons in conduction band of intrinsic semiconductor. Step number two is determination of density of holes in valence band of an intrinsic semiconductor. Step number three is intrinsic carrier concentration. So these are the three steps involved in this particular topic. So density of electrons, I can represent it with N. Density of holes, I can represent it with N. So my idea is by multiplying N with P, I would get Ni square, so that Ni equal to root over N into P. So this is the final intrinsic carrier concentration. To get this, I have to get N, I have to get P. So first let us calculate density of electrons in the conduction band of an intrinsic semiconductor. So we can calculate density of electrons in the conduction band of an intrinsic semiconductor by using this formula dN equal to Z of E into F of E into dE. Okay, so first of all, what is dN, what is Z of E into F of E into dE? Let us see. Here what I am calculating, this is the conduction band of an intrinsic semiconductor, this is the valence band, right? Once again, conduction band is a combination of so many number of energy levels. So here what I am considering, actually conduction band is not a box, it consists of so many number of allowed energy levels. Here my task is to calculate how many number of electrons are there in this conduction band. How many number of electrons are there in this conduction band? So that is nothing but N. But here I am directly not able to calculate N. So for this I have an idea. So I consider two energy levels. So for example, let us consider this energy level, this energy level. So I named this energy level as E, and I am considering another energy level. So what is this energy level? E plus dE. So E is lower energy level, E plus dE is little bit higher energy level. So you have different energy levels between E and E plus dE. Those are called as density of states. So what is Z of E into dE? Here Z of E into dE are called as density of states. So what are density? How many number of states per unit volume? So here Z of E into dE are density of states available between E and E plus dE. But in this example, we can calculate it as 1, 2, 3, 4, 5. So Z of E into dE is 5 in that case. But in reality, that is the not exact number. So you can calculate Z of E into dE by using this formula 4 pi by h cube into 2m whole to the power of 3 by 2 into e power half into dE. I hope you got clarity about the Z of E into dE. So the number of energy states available between E and E plus dE, those lines, how many number of lines are there between E and E plus dE are called as what? Density of states. Then what is F of E? Here what is F of E? F of E is, let us consider this is the energy level E. So what is the probability that, and suppose if you are supplying one electron to the conduction band, this electron may occupy this energy level, it may occupy this energy level, it may occupy this energy level also. So what is the probability that a electron can enter into this energy level? E is called as what? F of E. So here what is F of E? F of E is called as electron occupancy probability in an energy level E. So we can find f of e value as 1 by 1 plus exponential of E minus EF by kT. Here E is this energy level E, and EF is a Fermi energy, K is Boltzmann constant, and T is the absolute temperature. So the multiplication of density of states Z of E into dE with what? Electron occupancy probability will give dN. So what is this dN? dN is the number of electrons available between these energy levels E and E plus dE. So this is one electron, this is one electron, this is one electron, this is one. So all the electrons available between E and E plus dE is designated with what? dN. So dN is the number of electrons presented between E and E plus dE energy levels. Actually I want what? I want the electrons from here to here, which means from it, and in the entire conduction band how many number of electrons are there. So to do this, what we have to do? We have to integrate dN. So dN is the number of electrons in this limited energy levels E and E plus D. This E and E plus D is a small part of the conduction band. Okay. So if you integrate this dN, I would able to get what? N. So what is N? N is the total number of electrons presented in this entire conduction band. This is my core idea. So to do this, we have to integrate the above equation. Integration of dN equal to integration of Z of E into F of E into dE will gives the total number of electrons. So I can replace this integration dN with what? N. So N is the density of electrons in the conduction band. This is my idea. So what are the limits? Integral Z of E into F of E dE. So what is the upper limit? What is the lower limit? Let us assume that the least energy level in the conduction band is EC. What is EC? Lowest energy level in the conduction band. Okay. So the highest energy level in the conduction band is ECT. ECT. Okay. So you have to integrate this from bottom energy level to top energy level, ECT. So here EC is the bottom energy level, ECT is the topmost energy level in the conduction band. So ECT level. To occupy an electron in that topmost energy level, we require huge amount of energy. That huge amount of energy is taken as extreme. So that is plus infinity. So all the electrons are there in between bottom energy level to conduction band, to the topmost energy level of the conduction band. Here all the electrons are accommodated in between the EC to ECT. This ECT I considered as what? Plus infinity. Right. Now let us simplify the remaining things. So we can first simplify Z of E into dE. So where is Z of E into dE? This is Z of E into dE. So I can simplify the Z of E into dE for the case of semiconductors. So Z of E into dE is 4 pi by h cube into 2m whole to the power of 3 by 2. So I am converting it to the case of semiconductor exclusively for conduction band, 2m star whole to the power of 3 by 2. So here what else? E power half. So I can write e power half as e minus 0 whole to the power of half into dE. You may ask, what is m star? Here m star is called as effective mass of an electron. What is effective mass of an electron? If you go to the crystal, so this is a semiconductor, right? Maybe germanium is also a crystal, silicon is also a crystal. In the crystal the structure is like this. So there are continuous positive ions. A electron has to travel through these positive ions. These positive ions will create potentials. These potentials are called as periodic potentials. These potentials are called as periodic potentials. Whenever electron is passing through these periodic potentials created by the positive ions, what happens? The mass of the electron is changed, and that mass at that situation is called as effective mass of an electron. If it is whole, we can represent it as what? mh star. It is effective mass of whole. So we will use this mh star in case of when we are calculating density of holes, right? So the above equation become Z of E into dE, that equal to 4 pi by h cube into 2 me star whole to the power of 3 by 2 into, so E minus once again 0. So in the conduction band, already you have seen the least energy level is EC, not 0. Lowest energy level is not 0. Okay, lowest energy level is conduction, EC. Okay, somewhere here you can find E. Okay, so since E is greater, EC is lower, we can write E minus EC whole to the power of half into dE, or E minus 0. The least energy level in this formula we will get as 0, but here in this case of the conduction band, okay, when we are applying this formula to conduction band of an intrinsic semiconductor, in this case the least energy level is EC. So I am replacing this minus 0 with minus EC. So I simplified Z of E into dE for the case of conduction band. Similarly, simplify this f of E value to the case of conduction band. So what is f of E value? F of E equal to electron occupancy probability in an energy level E, 1 by 1 plus exponential of E minus EF divided by KT, right? Here do one thing, E minus EF is greater than KT. What does it mean? So your task is to calculate the how many number of electrons available in the conduction band. To happens this, a electron must break the covalent bond inside the valence band, and then it has to enter into the conduction band. Then only you can find the electrons. So it requires what? Outside energy. Outside energy, maybe it is thermal energy at a temperature greater than 0 Kelvin. So this outside energy, which is represented with E minus EF, this E minus EF should greater than the product of Boltzmann constant into temperature. If this KT is greater than if this supplied energy E minus EF is greater than KT, then only these covalent bonds will break down, then only these electrons enter into the conduction band, then only we are able to calculate density of electrons in the conduction band. So this is E minus EF greater than KT, then only we can find the electrons in the conduction band, right? So if E minus EF is greater than KT, then we can write E minus EF by KT greater than 1. If this value is greater than 1, then its exponential value is also greater than 1. Okay. If it is true, let us see this equation. So in this equation, what we got is this exponential of E minus EF by KT is greater than 1. So this is a smaller value, this is a larger value. Let it be 10,000, let it be 1. 10,000 plus 1. Once again we can approximate it to 10,000. So we can ignore 1 when compared with this exponential of E minus EF by KT value. So this f of E can be approximated to exponential of E minus EF divided by KT. So if you brought this E power value to the numerator, then it becomes exponential of EF minus E by KT. Okay, so I got simplified f of E value, I got simplified Z of E into dE value for the case of conduction band. Now just substitute those values in this equation. N equals EC to infinity Z of E into F of E into dE, right? So let us plug in the z of e into dE value in this equation. N equal to integral ec to infinity. What is z of e into dE value? This what we got. 4 pi by h cube into 2 me star whole to the power of 3 by 2 into e minus ec whole to the power of half into dE. So I can remove this value. Now I substituted this value. What about f of e? F of e can be approximated to this, which means into exponential of ef minus e by kt. So here this dE I am writing here and I am removing from here, right? So first bring out the constant values to outside. So 4 pi by h cube is a constant, 2 me star whole to the power of 3 by 2 is a constant. So 4 pi by h cube into 2 me star whole to the power of 3 by 2 is brought outside of the integral. So ec to infinity, e minus ec whole to the power of half into exponential of ef minus e divided by kt into dE. So I'll create some space. Once again this can be done like this. 4 pi by h cube into 2 me star whole to the power of 3 by 2 into integration of ec to infinity e minus ec whole to the power of half. So this can be subdivided as exponential of ef by kt into exponential of minus e by kt. So you can write e power a plus b as e power a into e power b. So this is e power a, this is e power b. This expression is in the form of e power a plus b, right? So bring this value outside of the integration because ef, Fermi energy, is the constant. Okay, so if you bring this to outside, this expression becomes e power ef by kt. So I can remove this value here. Once again I am writing the same here, minus e by kt into dE. Right. So to solve this integral, let us assume this e minus ec equal to x. So e equal to ec plus x. If you brought this minus ec to opposite side, you would get e equal to ec plus x. Then dE equal to dEc plus dx. Here EC is the lowest energy level in the conduction band and its energy is constant. So differentiation constant differentiation becomes what? 0. So this equation becomes dE is equal to dx since dEc becomes 0. Okay, so I got dE as dx. Slowly what I am doing to solve this integral, I am converting e's in terms of x. So this dE is converted as what? Dx. Now this EC, which is energy, and this plus infinity, which is the terms of E, should be converted into x. So for this apply the limits. So here what is the lower energy limit? EC. Okay, so by applying the lower limit in this expression, what we would get? X equal to E minus EC when E is equal to EC. When E equal to EC. Why? Because EC is the lower limit of energy. I am converting this EC in terms of x. So x equal to EC minus EC. Obviously x equal to 0. So this EC in terms of energy is converted into x as 0. Next, by applying the upper limit, okay, the above expression becomes x equal to E minus EC when E equals to plus infinity. Here what is the upper limit of energy? Plus infinity. So x equal to infinity minus EC, nothing but infinity. If you subtract something from infinity, once again you would get infinity. So E is converted in terms of x. So the above expression becomes n equal to, let us see this equation, n equals to 4 pi by h cube into 2me star whole to the power of 3 by 2 into exponential of EF by kT into integration of this EC is converted as what? This EC, when equal to EC, is converted as what? 0. So you should replace with EC with what? 0, and the upper limit is converted as what? Infinity. E minus, here what is there? E minus EC. Here we are assumed that E minus EC equal to x. So x to the power of half into exponential of minus E. Here E is there. So what is the E value? EC plus x. So EC plus x whole divided by kT into what else? dE. So this dE is nothing but dx. dE equal to dx. So that equation can be simplified as n equals 4 pi by h cube into 2me star whole to the power of 3 by 2 into exponential of EF divided by kT integration of 0 to infinity x to the power half into, you clearly observe this, we can subdivide it as exponential of minus EC by kT into exponential of minus x by kT into dx. So here once again you can bring this e power minus EC by kT outside of the integration. Why? Because EC is a constant value. So in the conduction band, the least energy level is named as EC. If electron is in that state, it possesses a constant amount of energy EC. So since this is a constant value, you can bring it outside. So if you brought this value to outside, it becomes what? EF minus EC by kT, exponential of EF minus EC by kT. So you can remove this. Now what we have? We have the integration of 0 to infinity x to the power of half into exponential of minus x by kT into dx. You can solve this integration by using gamma function, okay, as kT whole to the power of 3 by 2 into root pi by 2. So just plug in this value in the above equation. So the above equation will be turned as 4 pi by h cube into 2me star whole to the power of 3 by 2 into exponential of EF minus EC by kT into integration. This entire integration value becomes what? kT whole power 3 by 2 into root pi by 2. So these 2 cancels out in this 4 for 2 times. Next what else? N equal to 2 into, here 2me star whole power 3 by 2 is there. So 2me star whole power 3 by 2 is there. Similarly we have kT whole power 3 by 2. So kT whole power 3 by 2. So if you clearly observe, here we have pi to the power of 1, here we have pi to the power of 1 by 2. So if the bases are same, you can add the powers. So it becomes pi to the power of 3 by 2, right? Divided by. So everything is simplified here, okay? So what else in the denominator? H cube. You can write h cube as h square whole to the power of 3 by 2. So what happens now? This cancels out, this square and this by 2 cancels out. Then once again it will returns you h cube value. So you can write it as h square whole power 3 by 2. So what else? Exponential of EF minus EC by kT. So this is the expression for density of electrons in the conduction band of an intrinsic semiconductor. So